Welcome everyone to the second video in this 10-part series on convective wildfires. My name is Tisnarulos, and today we will discuss the environment in which convective plumes develop. As we have seen in the previous video, these environments are essential for understanding how these plumes develop. For this video, we will use this specific plume as a case study to understand how the atmospheric environment determines the development of plumes. And I realized that this figure shows a plume originating from a factory stack, not from a wildfire. Rest assured, during the other videos, we will dive into wildfires and see a lot of examples of wildfire-induced plumes. But for this specific video, I want to focus on the interaction between the atmosphere and the development of plumes. And that makes this an excellent example, because what makes this plume very interesting is the predominantly horizontal development of the plume without many vertical fluctuations. And the big question is, can we explain why? And to investigate that, we will first look into the atmospheric dynamics during daytime and nighttime. And then at the end of this video, I will hopefully convince you that using our knowledge of the atmosphere, we can explain the observed shapes of plumes that we see in the field, like this one, for example. Let's start with the daytime atmosphere, which means that we have a sun supplying energy to the land surface, which heats up the land surface. This subsequently means that we heat up the air directly above it. And from the previous video, we know that when we heat up air, it means that they become positively buoyant, meaning that they start to rise upwards. And if air starts to rise upwards, this air needs to be replaced, meaning that on the other side, also air will go downwards, creating a mini circulation above the land surface, which we very intuitively call the mixed layer. This is the layer where convective air particles rise and then go down again, creating this circulation. Sometimes near the surface in the lower 10 to 50 meters, we also see a surface layer developing, which has an even steeper decrease in temperature over height. And together, this surface layer and mixed layer is what we call the convective boundary layer, or in other words, the daytime boundary layer, meaning the layer of the atmosphere that is directly influenced by the land surface through these convective parcels that rise from the land surface upwards and then back down. You might ask, why do these parcels stop at the top of the mixed layer? And this is because during daytime, the mixed layer is capped by a so-called capping inversion, where the temperature increases with height. Meaning that if an air parcel rises further, here indicated by the orange arrow, it becomes cooler and thus denser than the environment, meaning that it will drop down into the mixed layer again, such that it inhibits further vertical rise. Above the capping inversion, we find the so-called free troposphere, which is free of influence from the land surface, and the exact properties are determined by the large-scale meteorology, but that's outside the scope of this video today. So this is the conceptual overview of a daytime atmosphere. So the next question is, okay, what happens when the sun disappears and we move towards nighttime? At that point, the energy input basically disappears. So at night, without the energy input from the sun, we see that the temperature at the surface starts to drop. And this also means that the temperature of the atmosphere directly above the surface drops. And this causes the development of a surface inversion, meaning that near the surface, the temperature increases with height, similar to the capping inversion. And this means, similarly, that when air parcels want to rise, that does not happen. Because when they rise, they become colder than the environment and thus more dense than the environment, inhibiting vertical rise. This layer, the surface inversion, is what we refer to as the nighttime or nocturnal boundary layer, and is known to inhibit any vertical motions. Above this, between the surface inversion and the capping inversion, we find the layer that is left over from the previous daytime. And we very intuitive call this the residual layer. This is the layer that is the residual from the previous day. Coming back to the initial figure that I showed of this factory plume, can we now explain the shape of this plume? The first thing that we have to look at is the time at which this is taken. This is taken at around 2020 local time, meaning that we are in a boundary layer that moves towards nighttime, meaning that we have the development of surface inversion. This means that any vertical motion is inhibited. And that explains why this plume mostly moves very horizontally without any vertical motions. And so we see from this figure that using our knowledge from the atmosphere, we can explain the observed plume shape. So to summarize, the atmospheric structure depends on the time of the day. During daytime, we find the development of a convective boundary layer that is well mixed, whereas during nighttime, we find the development of a nocturnal boundary layer, which instead inhibits vertical mixing. We have seen that using this knowledge on the atmospheric structure, we can explain field observations in the past. Eventually, the goal of this series is to go to predicting the type of plume that we will find in the future. We will do so from video 4 onward, with Brian Verhoeven as the host, but in the meantime, I want to introduce you to clouds, as this is the missing ingredient that we have not yet discussed. But we know from field observations that plumes sometimes lead to the development of pyroclouds, but sometimes they don't. So we will elaborate on this in the next video. Thank you very much for watching and see you next time.